So I want to just lay out for you the parallel structure and then see if I can't at least motivate. We're not going to be able to derive until we go to a vector treatment of angular momentum. But I want to show an example so that you're persuaded about the parallel between the expressions that we have for translation and that we're developing for rotation. So momentum is, of course, the product of mv, and the rotational analog is that the angular momentum is the product of the rotational inertia times the angular velocity. The net force on an object causes, that equals, remember, causes a change in the momentum, F equals dp dt. And the analogous statement that we're going to try to investigate is that the net torque produces a change in the angular momentum. And similarly here, when we worry about something whose mass is fixed, we can factor out the mass in the momentum. It isn't affected by the derivative, so we have mass times the derivative of the velocity with respect to time, or F net equals ma. And the analogous thing for an object whose shape is not changing when we operate on it with a torque is that we can factor out its moment of inertia and get that the torque causes an angular acceleration. So alpha is the Greek analog of a, and so that's the derivative of the angular velocity with respect to time. Okay, so that's the claim, and now I want to see whether I can at least persuade you that this follows from that in a special case. So here's the case. I have a mass point that's constrained to move around a circle of fixed radius. Okay, and I'm going to pull on it in some crazy direction with a tension force T2, and T2 is, I guess, makes the angle phi with the radial direction at this particular point, and we can describe with angle theta the position of the mass point as it goes around the circle. So I would like to see is tau equal to I times alpha consistent with what I know for starting that's the question. Can I start with F equals ma and deduce that the torque causes this angular acceleration? So back on Thursday before the break, to your horror, we derived the following expression. Remember the good times? Oh yeah. Oh yeah. And so far, before talking about orbits, we only worried about that term, which if an object is moving around in a circular path at constant angular velocity, well, if it's going around in a circle, then its radial distance is not changing, so r double dot is 0. So we had this term. R dot was 0, that one's gone. And if it's going at constant angular velocity, theta dot is non-zero, but theta double dot, the derivative, is 0. And so the only term that we needed before was this one, which is the acceleration towards the center. But in general, if things can move both radially and around in the theta direction, then we need all 4 terms. In this example, however, the mass point is going to be constrained to move around a circle, and so I can get rid of this term, and I can get rid of this term. Now, in order for it to be constrained to move around the circle, there will, in general, need to be a tension force or some sort of force that's radially inward this way. And so I now would like to apply F equals ma to this particle and see where that leads. Is there any question, okay, about what the theta hat unit vector means? Are you good with that? So a unit vector in the theta hat direction would be this way, and a unit vector in the radial direction would be like that. Okay? So F equals ma means that the sum of the forces, T1 plus T2, must be equal to the mass m times that junk, except that I already wiped out half of it, so it's not as bad, minus r theta dot squared in the r hat direction, plus r theta double dot in the theta hat direction. I have a typo. I need to hit Control T and transpose. There we go. Okay. So, thank you. So, at this point, I mean, this is two-dimensional, and I have 2 unit vectors, but I only really care about one. Which one do I care about? Which direction? Yeah, just the theta direction. So can you resolve T2 into its theta component? So T2 T2 should be the magnitude of T2 with the cosine of phi in the r hat direction and the sine of phi in the theta hat direction. Agreed? So if I take my equation F equals ma and require that it be true in the theta hat direction, I get that T2 times the sine of phi must be equal to m times r times the second time derivative of theta. Agreed? And the question is that consistent with the torque causes I alpha? So I want to look at this. What do I need in order to convert that into the moment of inertia? Yeah, why don't I multiply both sides by r? So then I have r times T2 times sine phi is equal to m r squared theta dot, double dot. So this is I times alpha. And what's that? Is that the torque about the center. So at least in this case, it's consistent with, that is, torque causing the angular acceleration or the time rate of change of angular momentum is consistent with F equals ma. And we will see in a couple of chapters, I think it's chapter 20, that we can show this in general using vectorial methods. Okay? Question on this before we do an example. Yes, please. Why did I get rid of T1? Hannah, why did I get rid of T1? So what is the component of T1 in the theta hat direction? 0. Yeah, so I'm just resolving. If this is true, then by components it has to be true as well. And so I'm just taking the theta component.